Thank you very much. So let's go to the next talk. The next speaker is Chiara Signorile-Signorile, and she will tell us about precision calculations for collider physics, the subtraction contribution. Please go ahead.
Thank you very much for the nice introduction, and I would like to thank the organizer for giving me this amazing opportunity to talk a little bit about subtraction schemes and their contribution to precision calculation for collider physics. So in the next 20 minutes, I will try to answer the question why the Amplitudes community should care about infrared subtraction. So I know that it is a bit a kind of, let's say, unusual topic for Amplitudes, but I still think there are some interesting aspects to discuss. So let me start with some motivations. We know that thanks to the collinear factorization theorem, hard collisions at the LHC are described in terms of quark and gluon cross-sections. And this way we are able to separate a non-partition section that can be computed in perturbation theory. So it is very important to stress that fixed order prediction represents one of the pillars for precision physics at the LHC. So expanding in terms of the couplings, this partonic cross-section, we see that NNLO QCD is rapidly becoming the required accuracy standard. But it is also true that mixed QCD electroweak corrections are also becoming extremely important to match the experimental precision. There is another important fact. We know that LHC continues to confirm the standard model prediction, and it is true for an amazing wide range of energies, and therefore one of let's say the goal for theoretical prediction is also to hunting very small deviations from standard model prediction that can be some, let's say, trace of beyond the standard model physics. So the importance of high energy theoretical prediction is essentially proven by the amazing numbers of computations that have been done in the recent past at NNLO. And I mean, this kind of revolution very recently is undergoing a second, let's say, phase, the so-called entry LO phase. And I would strongly encourage you to have a look at the talks by Bernard and by Gerardo for further details on N-cube LO computations. So in the last 8 months, already 3 important papers appear on the archive, and we also see that some attempts to study N4 LO are also appearing very, very recently. So one of the reasons that, thanks to which this is possible, is the treatment of infrared singularities. So we know very well that next to leading order quantities receive contribution from a double real correction, a real virtual term, and a double virtual correction. These are 3 different objects that have very different peculiarities and features. So for example, the double virtual, if we decide to use dimensional regularization, is affected by explicit poles up to 1/epsilon to the 4th power. So a lot of different progresses have been made in the recent times to compute virtual corrections so that almost all the relevant amplitudes for 2-to-2 massless processes are already available. And also first results for 2-to-3 amplitudes are now appearing. And for further details, take a look at the Simon's talk that is really, really nice and full of details. I would like, on the other hand, to focus on the double real contribution. And the main problem of the double real is that it is well defined in 4 dimensions in the bulk of the Lau phase space. But this is also affected by infrared singularities arising upon integrating over angles and energy of the radiated partons. So The main goal of a subtraction scheme is the following. We would like to extract these infrared singularities coming from the phase space without integrating over the full phase space. The reason for that is the need for fully differential prediction for infrared safe observables. So once these singularities are extracted, they can cancel against those stemming from the virtual contributions. So one of the main questions is the following. Can we complete this kind of wish list in full generality? And in principle, there are some evidences that suggest that the answer is yes. So for example, phase space singularities, as well as the virtual correction, and especially their pose, are known independently on the art subprocess. So in principle, one may think that the answer for can we do it in full generality is obviously yes. Well, in principle, this is true, but in practice, this is highly non-trivial. And two main methods have been implemented here called slicing and subtraction. And I will focus on the subtraction part. So the idea behind the subtraction is extremely simple. We have a quantity that is affected by phase space singularities, and this is a complicated object. We want to subtract the infrared singularities, and we can do it by introducing a so-called counter term. So this is the quantity here that essentially mimic the infrared singularities of the real radiation locally in the phase space. So of course, by construction, this term here is now finite and can be computed numerically by, I don't know, using Monte Carlo algorithms. Of course, we don't want to change the initial, the value of the left-hand side. So once we have subtracted this object, we have to add it back. And this can be now computed analytically, and we can easier, let's say, extract this explicit pose. So looking at a bit of the history, in the 90s, two main schemes appeared to solve this problem, and they are called the Catani-Seymour subtraction and the FKS subtraction. They have a completely different philosophy, but the key aspect, the key point is that they are fully general and they are already implemented in efficient NLO generators. So the problem of subtracting infrared singularities and NLO can be considered solved already 20 years ago. So what about the next? Well, at this level, of course, the problem is much more complicated. And in particular, the double real radiation and the extraction of these phase space singularities was really a bottleneck in the past. So just to give you an idea, today we have several, so numerous subtraction schemes. Some of them are really well tested and available. And I would like to stress the presence of this nested soft collinear subtraction, but also new strategies have been explored. So the reason for that is that we are still looking for the best possible subtraction scheme. So why we are still talking about subtraction is that we are still looking for the optimum solution for the subtraction problem. So we are still looking for a method able to accomplish these 5 requirements. So the so-called 5 criteria. So the perfect scheme has to be physical transparent, general, local, analytic, and efficient. So the question is, why is it so difficult? Well, making a step back to the schemes implemented next to the order, we can realize that, of course, although they are quite general and efficient, they still have some not optimized aspects. So, for example, the Catani-Seymour, which is based on the philosophy of creating a kind of interpolation between soft and collinear singularities for all pairs of partitions that can become resolved, is intrinsically based on a counter term that has a complicated structure. We also have the FKS scheme that has a completely different approach. The idea is to, for example, I will give some details in the following, on the idea of partitioning the phase space in order to simplify the huge initial problem into sub-problems that are much easier. So although we have two methods at NLO, still we are looking for a perfect method at NLO. Of course, it's not enough to have a method. We also need the crucial ingredients that in this case are the NNLO kernels that were already available 20 years ago. And I will just really briefly remind you of their, let's say, form. So essentially, the idea is that under infrared limits, a double real matrix element factorizes universal kernels and the lower multiplicity matrix element that can be related by spin or color correlations. But the crucial point is that these splittings or these aconal factors are universal, are essentially process independent. And the form for these kernels, I just want to quote them here just to have a little bit the idea of these functions that are not something mysterious. So they are essentially a ratio of Lorentz invariance and energy. These kernels have to be integrated over a 6-dimensional phase space. So giving a short answer, why NLO is difficult? Well, the point is that we have to essentially have a clear understanding of which singular configuration do actually contribute. And we have to get to the point where the problem is really well defined. And finally, we need to solve these phase space integrals that are definitely non-trivial. So let me start with the beginning. So we need, first of all, a clear understanding of which configuration do actually contribute. This is not, let's say, a super trivial problem, because some years ago, for example, one of the subtraction schemes that were implemented, called the stripper, it was essentially based on the idea of taking into account all the possible orderings of soft and collinear limits. And this is a quite complicated business that, thanks to color coherence, is in the end not really necessary. So I just want to stress that all the limits that I will mention in the following are understood to be to commute when acting on the real matrix element. And this is true thanks to color coherence. That is a crucial ingredient that is extremely useful to design a minimal scheme. Of course, this is not the solution for everything. So given this very simple diagram, if we write down the Feynman rules, we immediately realize that there are several possible singular limits, and they also overlap in the phase space. So I just want to stress, for example, the collinear sectors. So in the collinear singularities have several different possible configurations to appear. And in particular, in the triple collinear limit, we also have to consider strongly ordered configurations. So the cases where two among the three partons becoming collinear are more correlated than the others. And similar is also true for the soft, where we can have one parton becoming more soft than the other. So of course, at this point, we have several singularities. They are going around the phase space. We need a way to organize them. And one of the possible solutions is, as I mentioned, a phase space partition that essentially is, this idea is taken from the FKS scheme. So in this slide and in the following, I just would like to present you two possible approaches. One is implementing the nested soft collinear subtraction, and the other one in the analytic sector subtraction implemented in Torino. So nested soft collinear subtraction intrinsically is based on a generalization of FKS. So essentially it's based on the idea of partitioning phase space using angles and the angles of the partons emitted by the scattering. So the idea is very simple. We start from 1, we insert the partition functions, so functions able to enhance or dump some singular configuration, especially in the collinear sector. Once this is done, we are able to recognize a triple collinear sector, this 5161, the equivalent for level 2, so 5262, and two double collinear sectors. So as I mentioned, we have the problem of strongly ordered configurations. So the idea is to subpartition this triple collinear sector, introducing all the possible orderings of let's say nice variable, this eta, that is related to the angle between the particles. So one of the advantages of this approach is that it's intrinsically minimal, in the sense that given the process, with this approach, we are able to include all and only the sectors that we really need to treat all the phase space singularities. One of the main disadvantages, on the other hand, is that it's intrinsically not Lorentz invariance. So, I mean, this is not a disadvantage of the method. On the opposite side, we have what was done by local analytic sector subtraction, and the idea here is to preserve Lorentz invariance and including, so implementing a phase space partition sought to be able to essentially be modeled on an arbitrary number of partons in the phase space. So this idea is really nice. The main disadvantage here is that, of course, in order to be is not really minimal, in the sense that given the process, with this approach, there are also some sectors that are not really needed, or that can be, let's say, can be merged with other sectors. So, for example, in this case, for a plus and minus into QQ bar plus 2 gluons, we have 72 sectors. So it's quite a remarkable number of sectors. So at this point, what we have seen is essentially that the double real, we are able to design a counter term that mimic the singularities of the double real sector by sector. So we are able to select a specific number of singularities in order to simplify this subtraction. Of course, by construction, this contribution here is now finite in the phase space and can be computed numerically. I just would like to quote here the explicit expression for this term in square brackets, according to the nested soft collinear approach. And in my opinion, it's nice to see how, at least at this level, so at the formal level, the subtraction really look like something quite physical transparent. So the idea is that starting from a process, we have to subtract all the singularities, and we are including sector functions to introduce a minimum number of them sector by sector. Talking about analytic subtraction, of course, as I mentioned before, this is a scheme designed to be fully general, so I will not be able to write in just a few lines the same thing with the local subtraction, but the idea is exactly the same. So the last ingredient of this subtraction, as I mentioned you, is the integral over the unresolved phase space of the counter term, where I remind you that the counter term contains all the singular limits of the real metric segment. So the main structure for this integral is the following: is a phase space integral over the unresolved partons, a limit, and some constraints, where the limits are essentially the kernels that I showed you before, on top of other limits that arise after combining soft and collinear singularities. So these limits are universal, but the constraints and the phase space, or at least how we parameterize the phase space, strongly depend on the subtraction scheme we are dealing with. So in the next 2 slides, I just would like to present very briefly 2 different approaches to this kind of integrals. And in particular, I will focus on one of the most difficult integrals that we have to compute, which is the double soft counter term. So I remind you the explicit form for the double soft current. And as you see here, it is a combination of Lorentz invariance. And according to the nested soft collinear, what we have to compute is this object here, where the phase space is the Lorentz invariant phase space, with some constraints on the energy. So the crucial idea at this point is that one of the possibilities to solve this integral is trying to map this object onto loop integrals. And this can be done by using reverse unitarity and then integration by part identities and differential equations. So the answer for this object is, in my opinion, still quite compact. And of course, since it's based on the idea of having the dependence of energy and angles, it is a function of the angles between the hard emitters. So similar result is also valid for collinear, for the triple collinear kernel. Of course, the explicit result is different, of course. I would like to spend a couple of minutes discussing another completely different approach, that is the one we used to deal with the local analytic subtraction. So the idea here is to simplify as much as possible the integration by adapting the phase space parameterization to so essentially a soft kernel that depends on two hard emitters and two soft partitions is parameterized in such a way that we are indeed writing the phase space in terms of the same Lorentz invariants that appear here in the kernel. How this is done is essentially by introducing Catani-Seymour variables and writing this radiative phase space in terms of these quantities here. We can then use the phase space symmetries, partial fractioning, and hypergeometric function properties in order to get a very simple and compact result. I have to say at this point that the idea of introducing the so-called mappings, which essentially is a combination of, is essentially a combination of momenta, is extremely useful. But it also has some advantages, let's say disadvantages, in constructing the counterterms themselves. But if you're interested in it, I can, of course, give you more details. So at this point, I would like to briefly conclude. The idea behind this talk is that I hope I convince you that subtraction scheme are necessary ingredients to achieve a precise theoretical prediction, and the effort to design an optimized subtraction scheme is still ongoing. So I hope I stressed enough that both the schemes I presented have advantages and disadvantages. So we are still trying to find something that has just advantages. So this is also to say that nested soft collinear and local analytic sector subtraction are two alternative methods that are quite efficient, in my opinion, and are trying to accomplish all the 5 criteria. Although, again, still a lot of work can be done to optimize them. And I would like to conclude saying that phase space integrals are something that I think is quite interesting for the amplitude community, and they are a crucial ingredient for all the subtraction scheme. And with this, I would like to thank you for the attention and wait for a question.
Okay, thank you very much, Chiara. Let's thank the speaker. And we can take questions. Francesco, please go ahead.
Hello, hi there. Thanks for the talk. I just had a very probably naive question about one of the 5 criteria. Can you hear me? Sorry. Yeah.
Yes, sure.
So about the 5 criteria that you mentioned for, and one of them being the analyticity, so it being the formula being analytical. Has that to do mostly with for computational reasons, or is it also because we expect to just inspecting the formula, we expect to have a better understanding of the amplitude itself, or is it mostly just because it makes computation more efficient?
Well, exactly, it is the second one. Yes, yes. So it's more efficient. Yeah. Of course, in my opinion, it's also nice to try to do this kind of integrals analytically, because of course you are forced to, let's say, try to explore several procedures, several techniques. So from my personal perspective, something interesting per se. But yes, it also some, let's say, practical reasons.
Okay, thanks.
Enrico, do you want to ask?
Yeah, hey, thanks for this very clear talk. I have one question. In your nested collinear and soft subtraction, is it clear that is it true that you can only work in dimensional regularization and it regulates all divergences, or do you need like some analytic regulator to have? Do you have some sort of like what do you call it, rapidity divergences in this scheme or in this like computational setup that you have to separately deal with, which makes the computation harder?
No, I think it's enough to deal with the dimensional regularization. I think it's enough, yes. But this is also true for the the local analytic sector subtraction, which is the other method that I mentioned.
Okay. Thanks.
You're welcome.
Okay, so if there are no further questions, let's thank Chiara again.
Thank you very much.